Hello, my name's Mike Heap from the University of Strasbourg in France, and today I'll talk about the results of a couple of collaborative studies explaining the comprehensive list of co-authors on the tensile strength of volcanic rocks. To briefly explain why this is important, the tensile strength of volcanic rocks is an important input parameter in a wide range of modeling, in volcanology, but also in the context of geothermal reservoirs. However, although data do exist for volcanic rocks, the influence of microstructural parameters such as pore size and shape and hydrothermal alteration on the tensile strength of volcanic rocks is largely unknown. To help fill this gap in our knowledge, we used two methods. First, we performed numerical experiments. In the example shown here, shown on the left, the rock is blue and the loading patterns are green. The black dots within the blue sample represent pores. The advantage of these numerical experiments was that we could vary the different microstructural parameters such as pore size and aspect ratio while keeping all other parameters constant, something that is very difficult to find in suites of natural samples. Second, and shown on the right, we performed laboratory experiments on rock samples collected from a variety of volcanoes, including samples that are variably hydrothermally altered. We'll first look at the influence of porosity and pore size on tensile strength. The graph on the left shows the influence of porosity. Here, all the points are individual samples or model runs, and the symbols are color-coded based on rock type. We can see that tensile strength decreases as a function of increasing porosity, from about 30 megapascal at low porosity down to a couple of megapascal at porosities above about 40%. We can also see that the range in tensile strength for a given porosity can be quite high. The graph on the right shows the influence of pore size. If we look at a constant porosity, we can see that increasing the pore size decreases the tensile strength. For example, at 25% porosity, the tensile strength is reduced from about 3 megapascal to about 1.5 megapascal as the pore size is increased from 1 to 2 millimeters. These next two graphs show the influence of pore angle and pore aspect ratio on tensile strength. Numerical experiments show that when elongate pores are orientated with their long axis parallel to the loading direction, at 0 degrees the sample is strong, whereas the sample is weaker when the pores are orientated with their long axis perpendicular to the loading direction, at 90 degrees. The influence of pore aspect ratio is a little more complex, as it also depends on the pore angle. What we see is that the influence of pore angle on tensile strength is increased as the pore aspect ratio is decreased. For example, at a low pore aspect ratio of 0.2, when the pores are really stretched, the tensile strength is reduced from about 4.5 megapascal at 0 degrees to about 2.5 megapascal at 90 degrees. Here we show a series of semi-empirical constitutive models designed for fragmentation but adopted here that can be used to predict the tensile strength of volcanic rocks. The effective characteristic tensile stress, T0, has been determined using compiled data for the tensile strength of volcanic rocks. Therefore, if the porosity is known, the tensile strength can be estimated using these models and our value for T0. Finally, we also explored the influence of alteration on the tensile strength of volcanic rocks using laboratory experiments. Experiments were performed on altered rocks from La Soufriere de Guadeloupe in the Eastern Caribbean, Merapi volcano in Indonesia, and Chaos Crags in California in the USA. The x-axis here is the weight percent of secondary alteration minerals, used here as a proxy for the alteration. The influence of alteration is important because rocks surrounding intrusions or heat sources in volcanoes and rocks within geothermal reservoirs are typically altered. We find that alteration can increase tensile strength when associated with pore-filling precipitation, but that it can decrease tensile strength when associated with dissolution and mineral replacement. Guided by our experiments, we also perform numerical modelling to look at how fractures develop surrounding a pressurized dike when the host rock is either weakened or strengthened by hydrothermal alteration. In our models, the dike is shown in red and the host rock is shown in grey. Our modelling shows that the host rock is more damaged and that the damage is much more diffuse when the host rock has been weakened by hydrothermal alteration. When the host rock is strengthened by hydrothermal alteration, less damage is generated surrounding the dike, and the damage is largely confined to the top and bottom of the dike. We also offer updated semi-empirical models so that the tensile strength of volcanic rocks can be estimated if the degree of alteration is known, rather than the porosity. To conclude, our study has shown that the tensile strength of volcanic rocks is influenced by porosity, pore size, pore shape, and pore orientation. We've also shown that the tensile strength of volcanic rocks is influenced by hydrothermal alteration. We hope that these new data and models will help modelers who require values of tensile strength for their modeling. So, thanks for listening. To let you know, the first study described here on the influence of porosity and pore geometry on tensile strength was published last year, and the study on the influence of alteration on tensile strength of volcanic rocks is currently under review. Thanks again.